Here we are now going to discuss about loss of transverse vibrations in stretched strings. Previously we derived the formula for fundamental frequency nu1 is equal to V by 2L, where L is the length of the string and V is the transverse wave velocity. We know that transverse wave velocity in terms of tension in the string and linear density is given by root of T by mu, where T stands for tension in the string, mu stands for linear density. Therefore, the expression for fundamental frequency can be written as mu1 is equal to root of T by mu, and this 1 by 2L can be written as like this, 1 by 2L into root of T by mu. So this is the expression for fundamental frequency of vibration of a stretched string. From this we can say that fundamental frequency depends inversely on the length of the string when the linear density and tension are constant. So this is known as first law of transverse oscillations. Similarly, this fundamental frequency of the stretched string depends linearly on the square root of tension in the string when the length of the string and linear density of the string are constant. Similarly, if you keep tension and the length of the string constant, it depends inversely on the square root of linear density. That is, when L and T are constant. So these three are known as laws of transverse vibrations of stretched string. That means the fundamental frequency with which a string can vibrate with the length, with the tension and with linear density. Now we will discuss about standing waves formation in closed pipe and in open pipes. A closed pipe is a pipe which is closed at one end and open at other end, whereas open pipe means it is open at both the ends. Now in a closed pipe, since one end is closed, when the waves traveling towards that end strike the closed end, they experience reflection there. So when they get reflected back, they overlap on the incoming waves. So due to superposition of incoming waves and reflected waves, standing waves are formed. Since the displacement at the closed end is zero, what we get here at the closed end is a node, displacement node. And here at the open end, the particles can have maximum displacement. So the amplitude will be maximum. Hence, that is amplitude antinode. So this is the displacement node. This is displacement antinode. Now we know from the formula for the position of nodes and antinodes from the one rigid boundary or from one boundary. In case of strings, we derive this formula. That is, the distance of a antinode from the starting point is given by n plus 1 by 2 lambda by 2. So here, if L is the length of the air column and for n is equal to 0, what we get is this one. That is, at a distance of lambda by 4, you will get a antinode. Therefore, if the pipe is in the air in the pipe is vibrating with this type of frequency, we call that as fundamental frequency. Due to the vibration of the molecules or the air molecules near the open end, the displacement will be maximum, and we get a big sound that can be observed using resonance air column apparatus. So when the air is vibrating in the tube with this frequency, we call that as fundamental frequency. frequency or first harmonic with which the closed pipe is vibrating. So we can derive the formula for the frequency of fundamental mode of vibration of a closed pipe like this. We know from this lambda is equal to 2L by N plus half. And from our formula for frequency, wave velocity by lambda. So using that is equal to V by 2L, and this N plus half will go to the numerator. So for N is equal to 0, that is what we get is mu naught is equal to V by 4L. So the frequency in the fundamental mode with which the air column in a closed pipe vibrates is given by V by 4L. In the second mode, as shown in this figure here, so always the open end must be antinode, the closed end must be a node. So in the second mode, the air column oscillates as shown in the figure, and using the same formula we can show that this new one, so that is first overtone, we may call it as first overtone or second harmonic. So in that case what we get is, that is, this is 3V by 4L. 3 times the frequency with which the fundamental mode. So this is for second harmonic, or here we call this as third harmonic. If you say this is the fundamental frequency or first harmonic, since it is a multiple of this, we call it as third harmonic. Similarly, we can show that if the air column is vibrating like this with 2 nodes inside, or we can say 3 nodes inside and 1, 2, 3 antinodes, then we say it is vibrating with in the third node or third overtone or fifth harmonic. So then you can write like this 5V by 4L. So if you observe all these frequency expressions, you can write a relation. If you say this is fundamental, this is the second harmonic, this is the fifth harmonic, it will be, that is actually third harmonic, fifth harmonic. So you can write formulas like this: V by 4L, here 3V by 4L, this is 5V by 4L. So therefore the relation will be 1:3:5, etc. That means a closed pipe can vibrate only with odd harmonics. So harmonics are nothing but multiples of fundamental frequency, and any frequency higher than the fundamental frequency is called as overtone. Therefore, if this is the fundamental tone, this is the first overtone, this is the second overtone, or we say that this is the third harmonic, this is the fifth harmonic. So this is in the case of closed pipe. So similarly we can discuss in the case of open pipe. In the case of open pipe, both ends are open. Therefore, the air molecules or particles here in the medium can vibrate with maximum amplitude. Hence, you will be getting antinodes at the displacement antinodes at the open ends. And in the fundamental mode, you will have one node inside the tube. So, the condition for the distance between two successive antinodes is n times lambda by 2. Therefore, we can write a formula like this: lambda is equal to 2L by n. Hence, fundamental frequency in this case can be written as wave velocity or wave speed by lambda. So that is nothing but V by 2L. This n goes to the numerator. So this is the formula. Now taking that n is equal to 1, taking n is equal to 1, we will be getting fundamental frequency, that is V by 2L. So when the air inside the open pipe is vibrating with that frequency, we call that as it is in fundamental mode vibrating with the frequency, that is called the first harmony. So in the second case, the air can oscillate inside the open pipe like this, which is having at the open ends antinodes and inside there is one antinode. So there are two nodes inside. In this type of vibration, the open ends have antinodes. There are two nodes inside. The frequency formula can be written as like this. It will be twice to the fundamental frequency actually, 2V by 2L. And in the next case, if it is as shown in the figure, vibrating with inside 1, 2, 3 nodes and 1, 2, 3, 4 antinodes like this, then that is called the third harmony, or formula for that is 3 times V by 2L. So if you observe the equations for fundamental frequency and higher harmonics in the case of open pipe, we can write like this: mu naught mu 1 is to mu 2 is equal to 1 is to 2 is to 3. Directly V by 2L gets cancelled and we will be getting 1 is to 2 is to 3. That means in open pipes you can hear all harmonics, both even and odd. Therefore, generally the musical instrument, piped musical instrument will have openings at both ends, just like in the case of a flute. The sound will be very melodious because the quality is good. Because of since you can produce all harmonics in a open pipe, the sound quality will be more. So in this way, you can derive expressions for different modes of vibrations of air columns in closed pipes and open pipes. So in this way, we can derive the formulas for different modes of vibrations in the case of stretched strings and in the case of air columns in pipes. Here, the important thing is when at the open ends, why we get antinodes means here the pressure variations are minimum, whereas at the closed ends pressure variations are maximum. Therefore, we get minimum displacement at the closed ends, maximum displacement at open ends. Now, there are three important long answer questions based on these topics. So, the first important long answer question is explain formation of standing waves in stretched string and derive the loss of transverse vibrations in stretched strings. So that is a very important question. So you just explain how stationary waves or standing waves are formed in strings and just write down the formula for the fundamental frequency of vibrations of the stretched string. Then you write down all the three laws. And another important question is how standing waves are formed in closed pipes. And you must briefly explain that when sound waves travel through the closed pipes, at the closed end they get reflected back due to overlapping of the incoming waves and reflected waves. Standing waves are formed, and when the frequency of the air column in the pipe matches with the periodic frequency of the sound waves, then a condition known as resonance takes place. Then you can hear a big sound. That is what happens in the case of a whistle, which is equivalent to a closed pipe. Now, due to formation of these standing waves, we get different modes. The fundamental or the minimum frequency with which a tube closed pipe can oscillate, or the air column in the tube can oscillate, is known as fundamental frequency or first harmony. There are other frequencies with which the air column can oscillate. They are called as higher harmonics, more than the fundamental. And another name is overtones. So the higher harmonics are multiples of fundamental frequency. In a closed pipe, you will be getting only odd harmonics. Similarly, in the case of open pipes, say at both ends you will be getting antinodes where the particles can vibrate with maximum amplitude. Here also the waves overlap. Why they are getting reflected at the open end means because of pressure difference. Inside the pipe, outside the pipe, there will be a pressure difference. So the waves undergo soft reflection. So after reflection, they may overlap on each other. That is, incoming waves and reflected waves, they will overlap, forming the standing waves. And in this case, you will get both odd harmonics and even harmonics. So the quality of sound will be good in the open pipes. So a question is there in the textbook, very important one, that is explain formation of standing waves in closed pipe and derive the relation between the fundamental frequency and higher harmonics. Similarly, a question will be is there on open pipes also. So in total, 3 important long answer questions you can understand by seeing these videos, and I will send you notes appropriate for these topics, and just copy down these answers in your notebook and try to learn it within this week. And the next week I am going to conduct a Zoom call to know how good these lectures are and how you utilized these video lessons. Later I will continue with another topic, that is how beats are formed, what are beats, how beats are formed, and what is Doppler effect. That is also a very important topic. So that will be explained in the next session.